So we have to determine the constants which appeared both in X and P. And now, by now, we have learned from the experience at the free particle level that you use the initial conditions. That is, you go to the t equals 0 and identify the x of t and p of t with the corresponding Schrödinger operators, because these two match at t equals 0. So at t equals 0, the left-hand side is x now. I drop x operator, that is Schrödinger operator at t equals 0. And what is the right-hand side? Right-hand side is just C2 operator, right? Because the first vanishes, sign vanishes, cosine becomes 1. Therefore, C2 is automatically determined. And what about the P at t equals 0? That's the Schrödinger P operator. And so it becomes m omega C1 operator, right? Because it is sign vanishes, C2, although we determined already, that disappears. So this tells you that C1 operator is P Schrödinger divided by m omega. And this one, C2 operator is X Schrödinger operator. They are operators, and Schrödinger operators. So if you substitute them in, then solution at xt, solution of x at t equals time t, is Schrödinger sine omega t plus, cosine omega t plus p divided by m omega sine omega t. And the second one, pt, is m omega times c1 is p Schrödinger cosine omega t minus m omega times c2. So m omega x Schrödinger sine omega t. So determined, we have been able to find x of t and p of t. So from this point on, whichever way you are going to use these solutions is up to you and up to the questions you have been exposed to. And I will stop it in here, and then eventually, after going through some of the further properties of Heisenberg picture, when I will pick up the operator solution of the Heisenberg, when I pick up the operator solutions of the harmonic oscillator, I will resort back to them eventually. But for the time being, it just is solutions. You can check the following. For consistency, you can take the p squared divided by 2m plus 1 over 2m omega squared times x squared, and indeed show that it is equal to what? It's equal to the Hamiltonian. And what is the consistency check? Hamiltonian should be independent of the time by default. So check. And that is a check of the consistency of this trivial set of mathematical expressions, but it would be fun. It shouldn't take too much. M omega squared x of t squared is equal to p Schrödinger squared over 2m plus m omega squared x squared. That would be fun to check. And that's a property of the Hamiltonian, right? It's independent of the time. It has the same value in all pictures. And if the explicit solutions that you have found verifies that feature, it's not something that trivial. So I invite you to do that check, spend a few minutes on it. I will pick it up later when I start discussing the operator solutions of the harmonic oscillator. But for the time being, I will like to address the eigenkets, base kets first, and then I will turn my attention to Ehrenfest theorem along the line. Ehrenfest, perhaps even, Ehrenfest theorem first, then the operator solution. Let me not deviate that much from the book. Okay. Eigenkets in the Heisenberg picture. Again, the general feature was are frozen and the observables satisfy the following condition. Well, slightly aesthetically, of course. Different version of this equation may be a bit suggestive. As I said, it's the same equation written a slightly different way. What is it? When you take this to the left, and then I over H bar, A with H. You don't need this, right? You don't need this. Okay, anyway. If you want, it is a Schrödinger-like form. Perhaps that's the only thing. IH bar d psi dt was for the Schrödinger equation for the states. It's IH bar d A dt. It's the minus H with AH. So you have to remember this. H was, as something multiplying the state from the left, was driver of the time evolution of the size. H entering with a minus sign in the front, as in a commutator, is a driver of the time evolution of the observables. It's not exactly in the Schrödinger form, of course, it's commutator, but anyway, it's suggestive, I guess. Now, let me consider the A observable and write its eigenvalue equation. Then let me act on it by the U dagger. Well, remember U dagger was e to the I over h4 with a plus. Instead of using different types of u's, one set of u for the time evolution, another set of u for these passage from Schrödinger to Heisenberg, I'm using the same u. Therefore, perhaps what is a little uncomfortable is the u dagger is entering. Because time evolution is e to the minus I over h bar ht. U dagger is plus. It is with this plus which you undo the time evolution from the states and carry it over. That's the reason why it's U dagger. So you shouldn't be really upset about that why something like dagger appears instead of without dagger. It is not to introduce too many U's. It's the same U I am referring to. The U in its original form is in the time evolution in the Schrödinger picture. So it is the inverse of it which I act on it. So when you act the entire equation by this U dagger, what do you have? U dagger of T, A, AI, AI, U dagger of T, AI. And then here you insert an identity, U dagger. You are free to do so. You are multiplying with an identity, right? What is this? This is now with this particular choice of the U. This is the Heisenberg operator, the same observable written in the Heisenberg picture. And this should be then is the AI in the Heisenberg picture, right? Okay. Question. States vectors are time independent in this picture. And the AI form a basis. This was in the Schrödinger picture, and we have transformed them to the Heisenberg picture, being eigenvectors of the observable A. So notice that eigenvalues stayed the same, but eigenvectors changed. Same eigenvalues. First of all, let's check whether this is a paradox, or is there something, an inconsistency in here. No. Why is that so? Because we have seen that expectation values are the same and should be the same in any picture, right? Expectation values are the physical things that you measure in the laboratory. So it should be independent of the pictures. Let's demonstrate that quickly so that we'll say that it's no wonder, because eigenvalues are the expectation values in this particular basis. So that eigenvalues do not change is not something strange, but it's very natural. That's what it should be. Let's demonstrate this. Suppose you have an expectation value of an expression like this in the Schrödinger picture, and we would like to demonstrate that it will be the same as, it should be the same as the value in the Heisenberg picture. These things should be the same, expectation values. So what is the left-hand side? All right, let me start from the right-hand side. Psi h, a h, psi h, right? That's what it means. You take both observables and states in the Heisenberg picture, and let's write down the definitions of these entities to relate it back to the Schrödinger. How do I do that? This one is U dagger times psi Schrödinger, and this one is U dagger A Schrödinger U, and this one is psi Schrödinger U, right? So what is it altogether? U dagger, U dagger 1, so you get psi Schrödinger A Schrödinger psi Schrödinger. The expectation values are the same, therefore eigenvalues should have stayed the same, but eigenvectors do change. Question. Being the eigenvector of a now time-dependent observable, observables are time-dependent, eigenvalues stay the same, so that there's no time dependence coming from here. It was time independent in the Schrödinger picture. It's time independent now. So if this is time dependent, these should be time dependent. So that's an important observation, which is going to play a crucial role in our discussion of the path integral formulation soon, and we may even comment upon it. So let me write that in mathematical form. AI T. Now put that T dependency in. Heisenberg is e to the U dagger T II, which is e to the I over H bar HT and AI. AI is in the Schrödinger picture, and AIT of H in the Heisenberg picture. If that is the case, you, of course, naturally expect that this obeys a Schrödinger-like equation, right? It acts on here, I over h bar, h, e to the I over h bar, ht on ai, times the derivative acting on the second factor, but second factor is time independent, therefore it doesn't bring any contribution. That's very nice, because then you can rewrite this as EAIT Heisenberg. And what do you get then? If you take this IH to the left-hand side, IH d by dt, AI of t, Heisenberg, is equal to minus h, AI of t, h. You may start screaming, did I make a mistake? You wonder, why do I fall into that? Compare this equation with the general Schrödinger equation, which was satisfied by an arbitrary state, right? Of course, these are in the Schrödinger picture. So AI's eigenvectors in the Heisenberg picture satisfy a Schrödinger equation, not exactly, with a wrong sign. So that's a wrong sign Schrödinger equation, this one. That will be very useful in demonstrating what? In demonstrating that you can get Schrödinger equation for the wave functions that's coordinates in any basis. Okay, we'll see what that is. But it's a paradox, apparently, seeming, because this is an arbitrary state vector which depends on time. And that's the eigenket, although it's associated with an observable which is, sorry, let me put it another way. Eigenket here in the Heisenberg picture carries time dependence, although all the state vectors in here have no time dependence. It is a paradox, okay. Perhaps that's the question I should address before moving away. Psi h. Let's introduce a complete orthonormal set. Let's write it in terms of bases. What are the bases that I can use? Expand in terms of bases. Okay. I'm in the Heisenberg picture. Therefore, what are the bases? Bases would be eigenvectors of an observable, right? I have put in the time explicitly. If I'm going to expand it in terms of a time-dependent thing, how could I get something which is frozen in time? That sounds like paradox, is it? Yes. But first of all, I need to check one thing. If originally, in the Schrödinger picture, they were orthonormal and complete, I should check whether those features carry over to the Heisenberg picture, correct? Let me check. What is the orthonormality? AI, AJ, let me use discrete spectrum, doesn't matter. in the Schrödinger is delta ij, right? In the Schrödinger. What is the orthonormality? This is the orthonormality, and this completeness is AI. AI is 1. Do they carry over to the Heisenberg picture? This is in the Schrödinger. I can use a quick trick of rewriting the Schrödinger expressions in terms of the Heisenberg using the inverse of that transformation, right? How do I do that? I write here AI, this left-hand side, AI can be written as AI of t Heisenberg times e to the minus I over h bar ht. Well, I think this is not a good spot to write it. I will move to the left-hand side. I guess that's too tight a place in there, so it is a very important, as I said, as far as in this context and eventually in the path integral context, this discussion, although simple, plays a crucial role. So what I'm doing is the following. I write the orthonormality. These are the Schrödinger picture basis vectors. If I drop them, no danger because I know what I'm doing. So these are AI t Heisenberg e to the minus I over h bar ht is this vector. And what is this vector? This vector is e to the plus I over h bar ht aj, right? I'm writing the inverse, that's the reason why it's plus t Heisenberg. So beautifully, we have demonstrated that in the Heisenberg picture, this new set, this time-dependent basis vector set are still orthonormal. If they were originally orthonormal, they stayed orthonormal, but you say, of course, what could be more natural than this? Because we were transforming them by unitary transformations, and unitary transformations are those transformations which preserve norms. So it was a nice, quick check of something that we already knew. But how about the completeness? It looks a little less trivial. No, it's not that bad. So let me write the completeness now. This was the orthonormality. Completeness requires that I have this expression, right? So let me replace them with the corresponding expressions. Actually, Schrödinger, Heisenberg to Schrödinger is plus, Schrödinger to Heisenberg is minus. Although the result is not affected, please correct this, okay? Schrödinger to Heisenberg is with the plus, inverse of the time evolution. This is then vice versa is inverse transformation, right? I'm writing the Schrödinger in terms of Heisenberg, so that's nice. So let me write these in. Again, from Schrödinger back to Heisenberg. This one is e to the minus I over h bar ht ai t of Schrödinger, and this one is AIT Heisenberg, sorry. AIT of Heisenberg and plus. Okay. The argument is, in principle, if A and H have no relationship, then the argument is rather tough. But if you take A to be a commuting operator with the H so that they can have common eigenvectors, for this argument it's needed, then these become EI from here, a pure phase, a number, and this becomes e to the I over h bar EI, a pure phase with the numbers. Numbers can be floating around freely, and that cancels against this. And then you get AI of t Heisenberg, AI of t Heisenberg. So the completeness is a difficult property, so it is more comfortably proven in this context. But in the other context, it's a little more involved, so I'm not going to discuss it. Okay, so if the basis I am using an operator which commutes with the Hamiltonian, so it's very comfortable. Thus, the lesson is this transformation from Schrödinger to Heisenberg retains the orthonormality and the completeness, and these can still be used as a basis. If it is used as a basis, let me expand an arbitrary state, psi Heisenberg is equal to psi Heisenberg, and here I insert AI of t h, the identity AI of t h, this identity insertion on psi Heisenberg. So what do I need? I need to demonstrate that IH bar d by dt psi of t psi h, I know it's frozen. We need to demonstrate this, and in light of the fact that AIT now change in time and they rotate in the opposite direction of the arbitrary state vectors, is the solution really. Because if I now move in IH bar d by dt psi h, moving in and acting on here and there, it's more or less obvious, right? IH bar d by dt AIH is the first term times that next plus AI of t Heisenberg IH bar d by dt AI of t psi of h. Notice that this first term gives you what? This first term gives you minus h on AI of t, h. And this gives you, from here, what? If you take the here, I erased the left-hand side. What was this? IH bar d by dt AI of t. This is what I have erased. If you take the conjugate of it, h bar, h is Hamiltonian is Hermitian, but there is an IH bar, so the sign becomes for this one plus okay. And as these are chosen to be a common eigenvectors of the H and A, therefore this is a number now, which is EI. They cancel because of this opposite sign. Okay. As I said, the proof is more comfortable when you are choosing the eigenvectors or the basis vectors as for an operator which commutes with the Hamiltonian. Okay, so it cancels and you get indeed 0. So this statement and that statement is not conflicting statements, and that's only natural, despite the fact that they are both vectors. One are arbitrary vectors, the other are basis vectors, and sort of this passive and active rotation. They behave oppositely, okay, in analogy with the three-dimensional space. Because of this wrong sign, vectors behave oppositely to the ordinary state vectors. Eigenvectors or basis vectors behave oppositely to the ordinary vectors. Now, in the remaining short time, I would like to comment upon the Heisenberg equations and the so-called R.I.P theorem. Equation of motion in the Heisenberg picture versus R.I.P. Let me write the equation of motion in the Heisenberg picture. Let me remind you. We have shown that it is dAh dt is I over h bar h ah t. Okay, this was the equation of motion. Whereas we have an equation satisfied by the expectation values. Let me work that expectation value equation out, and let's try to understand these two equations in relationship with each other. What is the expectation value, time evolution of expectation value? Well, when you have an expectation value, obviously, based on the previous discussion in the last couple of hours, we have seen that expectation values are the same in any picture. We can take them in any picture, they will have the same value. Let's consider this in the two pictures that we have seen. What is it? For example, in the Schrödinger picture, what is the d by dt A? It is d by dt psi Schrödinger A Schrödinger, psi Schrödinger, right? You take all these in that picture. In the Schrödinger picture, if A is an observable, they're like x, p, energy, angular momentum, then it will not depend on time explicitly. Other things like external electromagnetic field may be a function of x itself, but it may depend on time explicitly, so it is not a violation of the definition of the Schrödinger picture. It is the observables, x, p, energy, anything which are derived from the x and p. So what is it? This is explicitly d by dt psi Schrödinger, you act on that term first, times as and psi Schrödinger, plus psi Schrödinger, that's in the left, A Schrödinger, it's not acted upon because it's frozen, so d by dt psi Schrödinger. What is this and this? This one is IH bar, 1 over IH bar, sorry, 1 over IH bar, H on psi Schrödinger. This one. And what about this one? This one is, you go to the dual space, this one, minus 1 over IH bar, psi, and H. If it was, well, normally I would have taken the dagger of it, but H is Hermitian Hamiltonian, therefore it is this one. So let's combine everything. What do I get? I will do it in the left corner. So d by dt, I have taken everything in the Schrödinger picture, which comes out to be, in the right-hand side, I have all the way 1 over IH bar. In the left-hand side, minus 1 over IH bar. So IH bar. Psi H A. It is the term which is coming from this last one. There is a minus sign, I move the I up, plus becomes plus I over H bar, H times A psi. From here, move the I up, minus A times H. Schrödinger, 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 Schrödinger. So, I over H bar, expectation value, Schrödinger, H, AS, psi, Schrödinger. What is it? It is really I over H bar, expectation value of H, A, Schrödinger. If it is in the Schrödinger, it is this Schrödinger. Everything is picked in from the Schrödinger picture. H's are all the same in any picture, right? This is the derivation of the Ehrenfest theorem, picking everything from the Schrödinger picture. What if we have done it by staying in the Heisenberg picture? Let me do it. It's trivial. I apologize that I'm repeating such a trivial exercise, but it's nice to see it. If I repeat everything by staying in the Heisenberg picture, it would be d by dt states in the Heisenberg picture, observable in the Heisenberg picture, observable in the Heisenberg picture. Heisenberg picture states are time independent, therefore I have to expand this. What was this? This was U dagger A Schrödinger U, right? So the derivative moves in, acts on, and again this is time independent. This is U dagger is what is coming with the plus sign. So it is I over H bar, psi Heisenberg, H, everything else is AH. And second factor is coming with the e to the minus, because U is the time evolution operator, U dagger is the inverse of it. So minus AH, H, psi H. Again, this is I over H bar in the Heisenberg picture of H with A. Compare these two equations. And knowing the statement that all these things, whether it's Schrödinger or Heisenberg, they have the same expressions, and whether it is the A's directly or the commutator of A with H, so I drop this S or H labels, and I get a general theorem which is valid in any picture, which is d by dt, A expectation, observables now. As I said, if it involves more than observables, I have to bring in additional terms. If it is an electromagnetic, classical electromagnetic field as a function of x, for instance. So you see, I dropped the labels. This is independent of the picture. The expectation values are independent of the pictures. Therefore, this equation is independent of the picture. Now I can compare it with that. Let's compare. As an operator equation, this is an operator equation valid for only in the Heisenberg picture quantities A, H particle is a Heisenberg picture observable, but that is valid in any picture in terms of the expectation value is only natural. But the analogy is amazing. The analogy with the quantum theory and classical physics is made manifest, particularly at this equation of motion level, because that is in terms of in terms of the expectation values, that is valid for that's the classical analog, and the other one is, of course, quantum. Perhaps in the remaining few minutes, I can think of using that R.I.P theorem for finding from quantum to classical, going from quantum to classical, right? Because expectation values are what you have in the classical physics, what you measure in the laboratories. If you have, example, H, again, let me do it three-dimensionally, because if one dimension is too easy. No, let me do it one-dimensional. I'll assign you a private homework to do it three-dimensional. No problem. If you have a Hamiltonian of that sort, V of x, let's see the R.I.P theorem. What is the R.I.P theorem? R.I.P theorem is obtained by taking that A here. A could be taken as an x and p. So let me write the x first. D by dt of x is I over h bar expectation value of commutator of p squared b of x and x. That's the right hand side. U of x commutes with x, so it is p squared over 2m comes in p squared and x. I do this, for example, to do it as fast as possible. I'm doing it in the Schrödinger picture so that I don't have to worry about equal times. R.I.P theorem involves expectation values. I am free to choose any picture I like, which I demonstrated. I'm carrying out simply in the Schrödinger picture, not to worry about the time. So what is this? Minus 2i h bar p. 2's cancel, I over h bar cancel, so you have 1 over m p. So this gives you p is m times d by dtx. If you identify d by dt of expectation value as the velocity operator, so mass times the velocity operator is the momentum operator, again, which is recovering in the context of correspondence principle, a classical expression. Well, that's classical, right? Because expectation values are classical. You reproduce exactly the classical knowledge that momentum is mass times the velocity. Let me now pick the second. If A is P, d by dt, P is I over h bar, the expectation value of p squared divided by 2m plus the v of x, comma, p. That's the right-hand side. P squared term commutes with the p. It is only v of x term which you should compute. V of x, p. Let's compute that commutator before proceeding. What is that commutator? P, v of x. P operator, v of x operator. What is it? We just put here an arbitrary function, and on that function, p acts like I h bar over I d by dx. So h bar over I d by, now it's one-dimensional, so sometimes you may not care that much about straight or partial derivatives, but mathematicians would get very mad at you if you do that. It's one-dimensional, so you use straight derivative. D by dx, v on psi minus v d psi dx. This one is v d psi dx plus dv dx psi. This first and last cancel, and you have minus ih bar dv dx on psi. P on commutator V on psi, this on psi, you drop the psi, and so you have the commutation relations derived. This is how you derive commutation relations. Okay. So that's what I need there. P with Vx is minus IH bar, so it is V with P is plus IH bar. So let me continue from here. D by dx P is I over H bar, the expectation value of this commutator with a plus sign, IH bar, dV dx. I over H bar cancels, and this becomes minus dV dx. What was P? Let me use the first equation. D by dt is the left-hand side of P. P is m times d by dt of x. That's the left-hand side, new left-hand side now. Minus dv dx. Or this one is m d squared dt squared. X is minus dv dx. Compare. That's the Newton's equation, right? M dx, d squared x dt squared is the F force, which is the minus the gradient in one dimension of the potential, and this is obtained at the level of expectation values. Can you really reduce it further? Because that's the V of x fully, then expectation value. What if you replace the V of x expectation value and write it really as a purely classical thing? I invite you to think of it on your own. How do you write this? As minus d by dx of V of x. That would be more like a classical expression, that's itself, right? In order to really establish the contact with the lower Newton's equation. You see how powerful the pictures are in relating the quantum to classical. To finish in one sentence, if you open up new eras through phenomenological observations to get into new regimes, obviously you check whether your old laws are functioning, operating properly. If not, you change the laws. But you change the laws to include this new regime, which is the atomic region, atomic scale, 10 to the minus 10 meters and shorter. But that law is functioning properly at the macroscopic scale in sending satellites, for example, Hubble or Planck, to space. If that functions properly at that scale, then the new law in that regime, when it's extrapolated to large distances, it should agree with this because it's still working in here. And that is the demonstration that quantum laws, quantum equations of motions, when carried over to macroscopic scale, they function in terms of the averages, which are the classical counterparts of quantum variables. So that finishes our discussion for today of Heisenberg picture. Next week, we are going to pick up the issue that we have started with, simple harmonic oscillator, in which we have solved in the Heisenberg picture. I will continue that discussion by introducing operator methods, which will be quite useful eventually in the context of quantum field theory, that operator methods. So that's a good point to stop for today.